My name is Petteri Paatsila. I'm actually also from Silicon Labs. I'm kind of product marketing manager. I'm working for retail applications. So we'll talk about the Petteri advertisement with responses feature and kind of a large-scale testing with that. Kind of make it super interactive. Somebody have played hands-on with PAWR? No panic. No panic. It's a new feature. I will kind of take you through all that. Let's just get a feeling on the audience that where we are. We'll walk through kind of roughly next 30 minutes. I will actually go through first. Talk about what is the PAWR. Kind of everybody on the same page, and there's a kind of an interlink. It's not the same thing, but there's also Bluetooth ESL, kind of a profile and service, which is also defined by the Bluetooth. I will have a look on that also because that's related to the testing that we did. I will go through the test architecture and actually what we have done, what's the setup, and then there's actually 3 key tests that kind of define. It's not all about kind of I would say key 3 tests that define actually the network kind of a performance, and then I summarize it at the end. All right, we take a look on why did Bluetooth define this kind of a periodic advertisement with responses. Obviously, there's a need. First need is that there needs to be a standardized star network, which was not the case really before. Two-way standardized star network. Needs to have the capability to host thousands of nodes. I will come back actually later on that how many nodes you can actually call from one access point. Well, there's an encrypted advertisement data. I will not talk about that, but that's actually outside of the PAWR, one of the new Bluetooth 5.4 features. I will skip that from today, but it's important for the application that things are encrypted. And then kind of the last topic, which is super critical, is ultra low power consumption. That's really the key of the PAWR, why all this is done. Driver application, it is ESL electronic shelf labels. They need to have a standard, which has not been the case up to date. And when you go outside and go to your local store, most likely you start to see these electronic shelf labels. So you've seen them for a while, or you start to see them now. They're deploying really quickly. Well, I would like to remind also that this has been the driving application, but I think the PAWR network as such, it is really versatile and can be utilized in a number of different end applications. But in this case, I'm focusing actually on ESL. All right, so let's start to have a look on the PAWR. What is that? So first, yes, we have the laser here. First, there's kind of 3 different advertisement modes. We have, of course, advertising for connection. That's been there from the day one on Bluetooth. Just kind of you advertise to get connected, get your headset connected, and you're happy there. That's what works in the connection mode. Brilliant, awesome, job's done. Second is actually kind of a beaconing type use case, where the central device can be an access point, can be a mobile phone, is actually listening for the beacons, advertising data from outside. So that's regular but one-directional data. So you can't actually get the data back in a standardized way. So that's what was missing on Bluetooth up to now. Now we have the periodic advertisement with responses, and if we actually look how this thing works, it's exactly what the name says. This guy actually in the center, in the context of ESL access point, this is sending beacons. That's surrounding devices actually listening for the beacons. And there's a control mechanism how these devices can actually provide a response back to the access point. Everything is happening on kind of a tight time controlled manner, and that's actually the secret behind for the low power consumption, which was the first. When you go back on the previous slide, that was actually one of the key things that we need to achieve. But this is actually in the core what the PAWR is doing and what's the novelty of it. If we actually look inside the PAWR, or there's three key items to remember. First, you kind of start the PAWR train, so access point starts to define how is the timing parameters, how many kind of devices you need to support, how many kind of sub-events there is, how is the timing of all these sub-events. That will basically define for your network responsivity, how large it can be, what's the power consumption, and so on and so on. So that's kind of access point starts the PAWR train. And then there is actually, let me actually show on here. The fundamental timing is actually the periodic advertisement interval. Kind of that's like advertisement interval. Now it's just called a periodic advertisement interval. Inside of that interval, you can actually define the sub-events. There can be up to 128 sub-events. Kind of in the context of ESL, we would call those groups, those sub-events. And every sub-event actually can address 255 unique devices. So you can do the math. So now we have the number for it. When I started to tell that, yeah, you have thousands of devices, but okay, you can actually address more than 32,000 devices from one single access point to utilize the PAWR method. Obviously, the reality is that's way too high. We talk about much less than that, but we have the capabilities. There's kind of Bluetooth is not limiting that. When you look inside a sub-event, that's actually where the magic then happens. For example, we zoom in on the first sub-event. You can see that here's actually where the access point is beaconing. So it's sending a signal. It can be utilized for two key purposes. The first purpose is that keep the whole network in synchronization. Every device on a network will wake up. It knows when this sync message is coming. Will wake up, syncs all the clocks, goes back to sleep most of the time. Obviously, that message can also contain the data, and then the response feature actually kicks in. And then there is a kind of a Bluetooth ESL profile and service. There's a standardized way how these responses are being kind of a time and what order they are. But now each individual device on the network can actually respond back to the gateway. So now you have bi-directional network, which is really super low power and it's scalable. So let's have a look on the Bluetooth ESL, kind of the profile and service. Just one slide to get kind of a. This is the way to utilize the PAWR. If you look the Bluetooth ESL profile, I would say that two different operation modes. First operation mode is connection centric. No magic here, just a normal Bluetooth connection here. You do configure the devices over normal connection, and then when you do kind of context of ESL like image updates where you have a more data upload, or you do kind of OTA firmware updates, you take the device under updates state, which is just normal connection. And then second part, which is kind of the key and core, is the synchronized state. This is actually when all the devices are running under the PAWR train. Each and every device knows that when they need to wake up, when they need to listen, and if they need to reply back, they have to reply something back. They know how to do that. Obviously, highly power efficient, large scale, well scalable system. Well, there's a third mode also, which is kind of a normal connectable advertisement where you actually enter the state machine. And then also if something happens, something may happen sometime that things fall out of the sync. There's also a controlled method to actually bring back the devices through this unsynchronized status and push them back to get to be synchronized. So now we have the PAWR. We have kind of the context of the Bluetooth ESL application, how it's utilizing that. And by the way, one important point. Once we are on a synchronized status, we can send commands for the devices. For example, change image, blink a LED, do something else, what's the temperature. All that can be done within this synchronized status because we have bidirectional communication. In the testing here that we did, you need to select. There's a lot of parameters that you need to select with the PAWR. It's always a trade-off. It's super flexible kind of a way to kind of set your network responsivity, power consumption, scale. So we decided actually to start here. We use 2 seconds advertisement interval. So every 2 seconds, the same story starts again from the 0. We set the PAWR train to actually hold 76 sub-events. Those sub-events will actually fit in on this 2000 milliseconds advertisement interval. And then there is a couple things when you look inside the sub-event. First, you get this kind of TX signal from the access point. There is a response slot delay. Obviously, we are talking about IoT devices, and the processing power of those may be limited. You need to have time, especially if you ask to respond first. You need to have time to kind of process the response, push through the kind of a display update command, push through the kind of a LED command, or take the temperature and send it back. Then we have actually 23 response slots defined on this one. Well, it's not by accident. So it happens to be that when you use the Bluetooth ESL profile and service, the shortest command, 1 response slot, you can actually fit 23 messages coming back to the access point and fit these messages on access point message to the devices. So that's kind of how we came to this PAWR timing setup and network setup. So that's the core for the whole network. What is also important, you need to keep the synchronization. So you need to be sure that on link layer that's controlling the PAWR train, if there is a lot of traffic, when things start to happen on a large network, you need to be sure that you always keep the PAWR train running. If you lose that train for connection or something else, you lose the network, and then there's kind of advertisement chaos for a while. On the network kind of a setup then, now we have the basic network. We have 2 different kind of deployment and recovery test. We actually utilize for that 532 tags, utilizing all the 76 groups, 7 tags per group. Then for the ping test, I will cover that later on. The magic, we wanted to have all the 23 actually devices to respond. So we kind of allocated the groups, we allocated only 23 groups, so we can actually have a full kind of response back on that test. So we have 2 different setups. That's also flexible. Kind of once you have the network up and running, PAWR up and running, you can kind of play a lot with that one. If we look to the network test setup itself, that's also hugely important. That it's a pretty complex thing. Kind of performs on 4 different blocks. The first block, actually the first 2 blocks are running, in our case, they are running cloud. We have a cloud environment for that. Of course, you have the test setup, kind of the DUT programming. You're doing all the test case execution, data collection back, so on here. And then we have ESL access point. So we have the access point core, and then we have the ESL library that actually is running the Bluetooth ESL profile and mastering the radio. And then actually the radio itself, we command through an encrypted data link from cloud. and then we have kind of a network coprocessor mode. We are running Bluetooth 5.4 stack, and then this is in contact with all the devices on field. This is actually just a photo, how kind of what you expect to see when you get this kind of network testing. We have a farm of devices. We're rack mounted. It's basically based on our development kits. If you go and kind of look for our development kits, they will look like that. Nothing special there. But then it's a kind of, it's a raw power. Mount them on a rack and kind of do standard mounting, kind of scale it up. And by that way, we will have a realistic radio environment for all that PAWR testing. So that's crucial, super crucial that we are running this test in a large scale. In this case, we utilized about 500 devices for that, but we have capabilities to go beyond that. Obviously, when you put devices on the test, more it takes time, more it kind of it gets more complex as you grow that one further on. But that's kind of gives you a kind of image that what are we testing, how we are testing, and what are the results. Okay, now we come actually for the test cases themselves. I had 3 kind of core test cases. Let's run the first one first. We deploy the network. So obviously what's happening here is that we start 500 plus devices are actually advertising concurrently in close proximity. And then we take the devices one by one, take them through Bluetooth connection. We do configure them. And there's actually one kind of a Bluetooth feature I did not share up to now. We are pushing the devices to this PAWR train by periodic advertisement sync transfer past. That's a feature actually has been developed by Bluetooth already before, and that's being kind of utilize the benefit of that in here. Once all the tags are there on synchronized, radio environment is nice and calm. Everybody's just listening for the heartbeat coming from the access point. Everything is time synchronized. Of course, kind of, when we start, it's a lot of advertisement traffic. So it's important that you have efficient Bluetooth stack, efficient kind of protocol handling, efficient kind of collection of the scan results, that from all that kind of an RF mess, you make sense. And then you need to have good configuration process effective, that you actually get things done quickly. If we look at the results, that's actually just raw results. What we have here in this case, as I had 532 tags, 76 groups, and 7 tags per group. And then on just kind of read out the graph for you. So that's the deployment time per tag. And then there's the tag grouping and tag number. It's always in this case, we start from tag 0. That's where you get zeros here, but we have 74 groups on here. So what we can actually, first the results. Okay, you take the average here. You can see the average is, it's kind of bit less than 5 seconds per tag. Well, you figure out that in this case, we take one connection at a time. There is a lot of radio kind of airtime which is not utilized. We don't have a nice graph of that, but when we actually utilize 4 connections in parallel, we actually slash that from about 5 seconds to less than 2 per tag. So there's a really great kind of a benefit utilizing kind of the RF airtime or the available airtime in a better way. So what we see here is obviously kind of, I mentioned that there is the past. That you can see that the results are mainly grouped here, but there's kind of roughly 2 seconds interval. This is coming from the design decision that we use periodic advertisement kind of an interval of 2 seconds. So naturally these will group on those bands. All right, so now we know the kind of a starting mass, 500 tags. We can manage to get that under control. It's about 2 seconds a tag, or with these network configurations I mentioned again. It's super flexible. Different kind of setup will result to different end numbers and end times. If I take the next one, which is actually now we're in the heart of the PAWR, but as a test, it may be not so exciting kind of the outcome of that, because it's expected outcome. In this case, we start from the condition that everything is synchronized. The network is running there, and we actually in this case we call for each and every device on a network by a ping command. That's the shortest command we can have. It's the magic. We can have 23 of those on one call. So basically, in our setup, we can call all the tags, 500 plus tags in 2 seconds. So if you kind of look the results for that test, straight line. Okay, that's what you expect to see. Straight line here. So first of all, kind of if you look the timing here again, I just kind of zoomed in for the first two groups. It's easier to kind of follow, but it's the same thing. We have tags, groups, and individual tags here, and there's kind of a time that we actually get the ping command back. With it be, if you look the results, I mean, it's 2 seconds PAWR interval. Depends completely on the test setup. If this is way more than 2 seconds, the first one, something's wrong. But in this case, we got lucky that we are kind of almost when we send the ping command out, there was a PAWR actually TX that actually happened, and we get the responses back. And in this case, it's also visible here that, okay, there's a first group 23 responses, second group 23 responses, so we can access each and every tag on one advertisement interval. So responsibility of that kind of a network is really, really good. But I think kind of what is the more interesting thing on here is that this was expected. That is what should happen. But what's the power consumption? Kind of mentioned that the low power is key, and there is actually most of the time that the devices are on this kind of a synchronized mode and not even listening, getting ping back, but just kind of keeping the time being synchronized, waking up. We took a snapshot of the power consumption here. The first of all, let me explain the image a bit. This is kind of there's a current consumption on y-axis, x-axis we have time. So first, and this is the power consumption from the peripheral side, so-called ESL tag, for example. So first of all, we wake up and listen for the access points ping command, and this is used to keep the time on the network. And in this extract, we also respond back. So then there is a TX from the device, which is barely visible here because they're really close proximity on each other's. Rest of the time, guy is sleeping. Then you wake up again after PAWR interval, sync your clock, see if there's a messages. If we are using, in this case, our kind of Bluetooth kind of radio board standard devices, use the DCs, 3 volts. And actually what is, for Bluetooth perspective, what is important is the clock accuracies. Because obviously less you have clock accuracy, larger window opening is to be sure that you're actually catching the message at the right time. This test we use 50 ppm clock accuracy. You get average current consumption of 3.7 microamperes. Super low. You can immediately say from that result that you can run with this. Obviously depends on the rest of the application, but this is kind of where the application spends most of its time over the lifetime. We talk about ESL, but that would be mostly the same for most other applications. So you can have 10 plus years even this number actually, it's indicating that you go, depending on battery, more than 20 years of lifetime. So that's pretty impressive. Now we know that we can set up the network. Network is responding with PAWR, kind of ping commands, and then we know that it's ultra low power. So what if something goes south? Hey, it does happen. That's the third case. So network recovery. There's a standard way to do that also, which is happening by the kind of standardized Bluetooth profile and service. In this test case, we actually start from here again. Everything is running smooth on synchronized status, but then we actually pull off the power from this guy, from access points. We wait the timeout. All the tags are actually in unsynchronized status. Every tag starts to advertise again. There's hundreds of advertising tags concurrently on air. So if you would look the RF, it would not look that nice. It's a messy RF. You have 3 advertisement channels and there's hundreds of devices shouting. Then actually the test is then picking up these advertising channels. That happens through this update state. So we take a connection again is syncing it back to the PAWR, and then eventually when the test is done, everything is back under control, and it's low power, nice and neat RF environment. So look at that result. Actually, it's really similar to this kind of deployment test results. Probably with a comment that in this case, we are kind of skipping the phase of configuring the tags, creating a kind of a bond between access points already created. We have all the keys that are required, so you don't need to configure. You only need to pick up the tag, push it back to the PAWR train. The tag knows where it should be when it needs to wake up once the kind of a time zero is clear for it. So in this case, with the single connection, it's a bit more than 2.5 seconds per tag on average. And then with the 4 connections, the benefit, as we're not doing the ping pong traffic like we do in the configuration phase that much, the benefit of additional concurrent connections is less. So, but anyway, we are kind of way less than 2 seconds per tag. So that's kind of how it looks. I'd say 3 key use cases, and we can kind of prove now, first of all, that there is a standard. Awesome. So everybody can do it in the same way. It's a controlled way to do now kind of a massive star networks. In this case, yeah, the ESL was shown as a lead application for it, but in multiple of use cases can actually take benefit of PAWR. That's super important to know. There's a kind of major change on Bluetooth. PAWR as such is super flexible. How you set up the timings and really kind of there's no one right solution. There is kind of how you set up that. It's depending on your final application needs. Based on the testing, it's clear that's kind of a Bluetooth PAWR it's responsive for large scale network. It's low power, so it's good to go. So it's a mature. I mean, it's all brand new technology, but it's a mature for mass deployment. So that's it. That's ready for IoT installations, and that concludes my part. Thank you.